It's a lovely late summer morning here in Montreal. How about some math? So copy all this down. Horizontal asymptote. So horizontal line that a function is approaching at the extremes. So I can do a little picture here, give you an idea of what such a thing would look like. So you have maybe a horizontal line over here. That's not very horizontal, but I think you get my idea. And maybe I have another horizontal line down here. And in the middle, my function is maybe doing something like this, but then eventually it approaches this horizontal line. And you can cross. Okay, you can cross and then come back, and that's possible. And then approach down here. That is totally possible. So this dotted line here is a horizontal asymptote. And likewise this dotted line here. That's not an A. There we go. Okay, so let's do an example of finding horizontal asymptotes. Now what we'll do is we'll do a limit as x goes to infinity, and we'll also do a limit as x goes to minus infinity. And we'll see if we get a real number. And if we get a real number, then that will be our horizontal asymptote. So for example, this one right here, let's say the continuation hits at 6 here. Let's say this one here would be minus 9, why not? So this horizontal asymptote would be the horizontal line, y equals 6. And then this horizontal asymptote would be the horizontal line, y equals minus 9. Okay, I'll remind you that horizontal lines are of this form, y equals something. That's because if you think about every point on this line, the y value is always 6. Okay, let's do an example. The example is find the HAs. Find the HAs. Find the horizontal asymptotes for this function. F of x equals e to the x plus x squared. And then on the bottom we'll go e to the x minus x squared. So as I said, we'll do two limits. We'll do limit as x goes to infinity first. So limit x goes to infinity of f of x. We're going to do that one. And afterwards we'll do limit x goes to minus infinity of f of x. And they could be different. Okay, if I scroll up to what I drew before, you see here's where I'm doing limit x goes to minus infinity. Here I'm doing limit x goes to infinity. They could be different, and in this case they will be different. In this case they will be different. Okay, let's do x goes to infinity first. So we have limit e to the x plus x squared over e to the x minus x squared. Okay, I'm going to use a little trick here. Now I'm going to identify the dominant term in the numerator. Cancel that. I'm going to identify the dominant term down here in the denominator. It's e to the x. What do I mean by that? dominant term. The dominant term, what I mean is that e to the x is bigger than x squared for x large. Okay, if I have a large x, then e to the x is bigger than x squared. It's even better than that. Sometimes we do a double. We do a double inequality. So a double inequality to indicate that e to the x is much bigger than x squared. Okay, if you think about that, the exponential function grows a lot faster. So we're going to use a trick here, which you can do when you have a limit going to infinity or minus infinity. You are allowed to, I will allow you to drop non-dominant terms. You have to be very careful with this trick, okay? Can't always use it, but if your x is going to infinity and you have like something simple divided by something simple, then in this case you can do it. And I'll show you why shortly. So what do I get? So if I just drop those, so I just get e to the x over e to the x, right? Okay, this may seem a bit magical, but what am I saying? I'm just saying that when x is very large, these two things are negligible. They're so small. If you think about e to the power of a million compared to a million squared, they're not even close. Okay, e to the x is much, much, much bigger than x squared. So I just drop those x squareds. I just drop these x squareds. I'm allowed to just delete those, and I will not change the limit. Okay, having done that, I get limit of 1, which is just 1. So my horizontal asymptote is the line y equals 1. Okay, over here, I have to find the other possible horizontal asymptote as x goes to minus infinity. It's not going to be the same thing. Because the dominant term is different now. Think about e to a large negative number, so like e to the negative 100. That's 1 over e. And this is very small. Okay, so this guy is actually very small compared to x squared. So think about if you have e to the negative 100, that's a tiny number, but when you square a negative 100, you get a large positive number. So these two are the dominant terms. Okay, so my limit becomes x squared over negative x squared. So I drop the non-dominant terms. Okay, now I can do the division, and I get negative 1 here. And then the limit of a constant is just the constant. So the horizontal asymptote is y equals negative 1. So I got two horizontal asymptotes, negative 1 and plus 1. I want to, before I leave you, I want to talk a bit more about this dropping non-dominant terms. So why don't we do a little heading down here. Say, why can I drop non-dominant terms? That's a good question. May seem a bit suspicious to a certain person. Well, you could do this kind of the long way. You go, if I were doing, say, that first limit, what I would do is I would identify the dominant terms. I would identify the dominant term downstairs. So what I'm going to do here is just show you a bit more systematically why the non-dominant terms don't matter. So first step is identify the dominant term in the denominator, and then factor it out. Factor it out of the top, and also factor it out of the bottom. Excuse me. And what's the idea? Well, x is going to infinity. And we've already decided, and I hope you agree, that e to the x is much bigger than x squared when x is large. So what's going to happen to this fraction? Okay, so if I take something and divide by something much larger, what's going to happen? Well, this fraction here is going to go to 0. And this fraction here is also going to go to 0. And what I get is just, see how I get e to the x over e to the x here, right? Okay, so I end up in the same place that I ended up here. Okay, this is a bit more systematic here. Okay, I'm arguing that these fractions are going to 0. Maybe I could do a step where I, first of all, cancel the e to the x's to make this super precise. And then I would go limit, then I would go, now I can do my limit. Okay, this is going to be, on top I'm going to get 1 plus 0 over 1 minus 0, which is 1. Okay, so I hope you're convinced that dropping non-dominant terms is okay. So in the future, you can drop non-dominant terms. You got to be a bit careful. Got to be careful. There are cases where it just does not work. So I'll give you an example. If I have this particular limit, this one's a bit more delicate. Okay, I have a x in the exponent, and I have an x in the base, and you may be tempted to say that this 1 is the dominant term. So I have a sum here. You may say, oh, this is the dominant term, so I'll just drop 1 over x, which gets very small. No good. That does not work. The reason being is that you have a difficult and delicate thing happening here. You have this base is going towards 1. So the base is going towards 1, and the exponent is going towards infinity. And that is a very difficult thing that you cannot play with. You have to be more careful. Okay, it's weird. 1 to the infinity. So this is a limit of the form 1 to the infinity, and that's a weird one. It's weird like 0 over 0 is weird. Infinity over infinity is weird. And also infinity minus infinity. Okay, these 4 things here, or limits of these form, have to be dealt with carefully. Okay, but in simple situations, like this one, okay, where you have x is going to infinity, and you have just like the sum divided by a sum, okay, you can drop non-dominant terms. Also, when x is going to minus infinity, and you have a sum divided by a sum, or a difference, and x is going to minus infinity, I will allow you to drop non-dominant terms.